Cool. So we're looking at volumetric rendering using path tracing. This person, Zydak, I guess is the name. It was a little write-up about volumetric rendering and a volumetric or a GPU path tracer, mostly going over specific algorithms used, problems encountered, and solutions to these problems. Won't be discussing full implementation details like launching array, accumulating gradients, utilizing the GPU, and so on, because it's a huge topic on its own. We want to keep this as brief as possible. So this assumes you already know the basics of path tracing, and we'll only focus on the volumetric rendering part. I'm not showing any code because it's mostly just math, which translates to code directly, and implementation of the delta tracking is heavily dependent on the workflow of the path tracer itself. So pasting code snippets without context is just confusing. Pasting entire code of path tracer is too long. So the source is on GitHub. There's two main ways of rendering participating media. The first of which is to merge the array through the volume in small steps, evaluating the medium's properties at each step, and accumulating the transmittance in scattered light along the way. This is called, was commonly used in real-time applications like games because it's fast and easy to implement. This is not, however, how light behaves in the real world. It doesn't just travel in a straight line, so this method has a major issue. It's not accounting for indirect lighting or any kind of global illumination. So in reality, light bounces around and interacts with the medium's particles multiple times instead of just traveling in a straight line. It's called multiple scattering. That's exactly what's happening in the second method, called tracking. It simulates and tracks all interactions of a light ray with the medium's particles as it travels through it. These particles are, of course, way too small to simulate individually, so a statistical approach is used instead, where the decision to scatter, absorb, or continue is made at random based on some probability. It's more accurate, but also way more computationally expensive. Because it relies on random numbers, it's stochastic in nature, which means that the results can be noisy and require multiple samples to converge to a smooth result. And because rays can exit at any point in the medium, it nicely accounts for indirect lighting, not just direct lighting from light sources. So the goal is to track transmission and absorption in a more stochastic way. Getting good quality results with ray marching can be hard since it requires a lot of cheap tricks like fixed ambient lighting. So goal for this article is to actually do the multi-scattering. For now, let's assume the medium is homogeneous rather. So this is a uniform volume. They're described by two properties. There's an absorption coefficient, sigma, and a sigma A is the absorption coefficient, and sigma S is the scattering coefficient. And these are the same across the entire volume. The absorption coefficient defines how much light is absorbed per unit distance traveled in the medium, and the scattering coefficient determines how much light is scattered per unit distance. Together they define the extinction coefficient, sigma t, which is the sum. This is the rate at which the light gets absorbed or scattered as it travels through the medium, and that's given by Beer's law. Beer's law dictates how much light remains untouched after traveling a distance d in the medium. This quantity is called transmittance. So the transmittance for a certain depth is e to the negative sigma t times the d value, the distance. It's important when you need to know how much light reaches a certain point in the medium. It's useful for calculating direct lighting from light sources using nearest event estimation. direct lighting from the sun is kind of the idea there. And that significantly reduces noise and speeds up convergence.
Just nitpicky, I think it stands for next event estimator, but anyway.
Right. Yeah, yeah, for the direct lighting stuff, yeah. Yeah, or next event, or nearest event, something. Anyway, too many particles simulate individually, so probabilistic approach is to be used to determine how the light interacts. The idea is to sample random distance at which the next interaction occurs based on some probability. This probability is given by sigma t times e to the negative sigma t d. Distance d, which light ray travels through the medium, occurs, it's called the free path length. We want to sample based on the probability P of d. To do that inverse transform, sampling can be used, and d ends up being defined as natural log of uniformly distributed random number in the range 0 to 1 divided by the extinction coefficient. Once the free path length is sampled, the ray can be marched through the medium by this distance. At this point, the decision is made whether the interaction is scattering or absorption based on the ratio of scattering to absorption coefficients. The probability of absorption is the sigma A over sigma t. It's the portion of the extinction that refers to the absorption. And the probability of scattering is the sigma S over sigma t. To decide whether event is scattering or absorption, we get another random number. If this other random number is less than the probability of scattering, this event is a scattering event. Otherwise, it's an absorption event. Also note that if the sample distance exceeds the distance of the medium boundary, the ray exits the medium without any interaction. This boundary can be defined in any manner. For example, a simple axis-aligned bounding box or mesh. All you really need is the distance to the boundary. So if the event is absorption, the ray is terminated. If the event is scattering, we need a new direction based on the phase function. So phase functions are angular distributions of scattered light. Defines how likely light is to scatter in a particular direction after an interaction. Several phase functions commonly used in volumetric rendering, each with its own characteristics and use cases. Most common is the Henyey-Greenstein, and it looks like this in terms of the angle theta. It's the angle between the incident direction v and the outgoing direction omega. So this function defines probability of light scattering in a direction omega, where the angle between the incoming vector and omega is theta. So G is the asymmetry parameter. It controls anisotropy. So when G equals 0, scattering is isotropic, meaning it has an equal probability of scattering in all directions. When it's greater than 0, it has a bias towards forward scattering. When G is less than 0, backwards, so what we're illustrating here. The Henny-Greenstein phase function is widely used due to simplicity and the ability to model a wide range of scattering behaviors. However, it doesn't accurately represent Mie scattering, which is the scattering of light by particles that are comparable in size to the wavelength of light. So this is something that's behaving like the water droplets in clouds. Mie scattering has more complex angular distribution with both forward and backward scattering components. So there are some other approximations. Combining Henny-Greenstein with drain phase function. Okay, so it has, I'm gonna have to take a look at that. So they just went with the Henny-Greenstein for simplicity, I guess. To sample a new direction based on this phase function, random angle between the incident direction V and the outgoing direction omega is needed. Since we have the probability distribution, just like before, inverse transform sampling can be used. After doing that with the phase function, we get the following formula. So if G equals 0, we can just take the random number directly. If G is not equal to 0, we do some remapping based on the G term. Since this is for the polar angle, and the azimuth angle, I guess they're calling it here, it needs to be sampled also. That's about the incoming vector. It's kind of a roll term, and that's just uniformly distributed times 2 pi, because it's, the phase function doesn't really affect it. So finally, spherical coordinates can be converted to Cartesian to get omega. So they construct an orthonormal basis. So you have an angle about this. That's phi, and then theta is the one that's influenced by the phase function. So that's pretty much everything for the basic tracking algorithm. Go to step 1 and sample the distance along the new ray with the direction omega. You keep repeating this process until the ray exits the medium or gets absorbed. Each time a scattering event occurs, you sample a new direction and continue tracking from that point. Over multiple samples, you get a good approximation for how the light interacts. So the issue is that a lot of samples are needed, especially with high scattering coefficients. To help with that, next event estimation can be used to directly sample light sources, which greatly reduces variance and speeds up convergence. The other thing for uniform volumes, another thing that they can be used for is subsurface scattering. By making the surface transparent and filling the mesh with a volume with a high scattering and low absorption coefficient, the way light penetrates the surfaces, scatters internally and exits at different points can be simulated, creating a soft translucent appearance. This is particularly useful for rendering materials like skin or wax. The only thing that has to be changed in the tracking algorithm is the boundary. Instead of being defined by the axis line bounding box, now it's using a mesh. So it's relatively easy to implement, since all you need is the distance to the next intersection with the mesh. And then the scattering, you just evaluate with the tracking, see if it's before the mesh intersection. Okay. So heterogeneous volumes are more complex than homogeneous ones. They can have varying density across the volume. The contents are not uniform. So the same equations for free path length sampling and transmittance cannot be used. Instead, varying density needs to be accounted for. So there's a couple of different approaches. Regular tracking, the idea is to split the heterogeneous volume into smaller homogeneous volumes and perform regular tracking within each region. When the ray crosses into a new region, update with the new medium properties. It's relatively straightforward, but not feasible for high detail. Alternatively, you can use ray marching to step through in small fixed increments. At each step, evaluate the medium properties to determine whether scattering or absorption occurred. The amount of steps required will vary based on the density. It's hard to find a good step size. So more advanced technique is called delta tracking. The idea is to use a majorant extinction coefficient, so that's a sigma t value that represents the maximum extinction in the volume. So that's like a maximum density. Free path lengths are sampled using the majorant coefficient. And when an event occurs, an actual density at that point is evaluated, and based on that decision is made whether the collision actually happened or if it's a null collision. So null collisions are ignored, basically. Sampling continues until an interaction is accepted, or you leave the volume. It's more efficient than regular tracking, like they described earlier. And the ray marching. It's still computationally expensive if you have a lot of empty space. So, yeah, right. Delta tracking seems like the most promising approach. Right. Yeah, I guess I've heard of delta tracking, not as much with the regular tracking stuff. Yeah. So, density data, they're getting a volume from a VDB format, sparse volume data. OpenVDB does not have, I'm not entirely sure that's true. Can't really be accessed from the GPU. It's a version called NanoVDB. And that one, I think you can just upload as a buffer and traverse it. Yeah. Okay. So the actual delta tracking implementation idea is to fill the volume with fictional null particles, so the medium can be treated as if it's homogeneous with the extinction coefficient sigma t max. Think of it as filling the gaps with invisible null particles, so that we can just act as if the volume is homogeneous when in reality it's not. So free path lengths are sampled using this majorant coefficient. And when an event occurs, the actual density at that point is evaluated to determine whether or not it's a real collision or if you collided with a null particle. Finding the majorant extinction coefficient is pretty straightforward. You just iterate through all the voxels in the volume and find the maximum stored density. From that, you can compute the maximum value of sigma t from the scattering and absorption coefficients. So free path lengths sampled using the same formula, using natural log of a random number 0 to 1 divided by this maximum density value. So larger value of this coefficient or whatever makes this step size smaller. Correspondingly, lower density corresponds to a larger step size. The actual extinction coefficient, sigma t, can be computed using the scattering and absorption coefficients. So the probability of accepting the collision is sigma t evaluated at the distance. Actual extinction coefficient. Okay, I'm not sure exactly which part of that is the texture read. But okay, so they have another random number that's randomly generated in 0 to 1. Oh, right, no. So sigma t here is going to be the volume density that's sampled over the maximum volume density in the volume. So this is just kind of a 0 to 1 normalized density, basically. So if this new random number is generated and it's less than this normalized density, then this collision is accepted, and it is considered a real interaction. It's a real scattering event. Otherwise, it is a null collision, and sampling continues. So this is right. So this accounts for the null particles or whatever. The interactions where you don't have absorption or scattering. Okay. Yeah, another thing is transmittance calculation. In delta tracking, transmittance over a distance d can't be computed analytically. Like it can be in homogeneous volumes. Instead, you have to integrate numerically by simulating a path. So starting at the ray origin, free path lengths are sampled the same way as before, using this maximum extinction coefficient. For each sample distance, the actual density at that point is evaluated, and the actual extinction coefficient is computed. If the collision is accepted, the path is terminated, and the transmittance is returned as 0. If it's a null collision, sampling continues until the ray leaves the volume. Okay, yeah, so at their formulation, you're either absorbed or not absorbed. That's coming from the fact that their absorption logic just kills the ray. I think it's not absorbing energy from the ray. That's why they're saying that. So that's pretty much it for delta tracking. It's an unbiased technique that allows you to simulate light in complex media without needing to subdivide the volume. Still be expensive, especially when you have a lot of empty space. Since you're going to be sampling a lot of low density volumes where this value will be very low and your random number check will not pass. Right. Unfortunately, this is visible as soon as you try to render something with it. Yeah, especially the atmosphere and clouds. You have a lot of empty space there. So they have a giant volume for a cloud. I think you'd probably be better served using something procedural. But you can do that however you like. So they're doing an anisotropy of 0.9 for strong forward scattering. Okay. So using delta tracking, they took 248 seconds to compute this, and that's only doing 10 samples per pixel. Still leaves a lot of really bad noise. Only a single cloud, blah, blah, blah. So we need some optimizations. The first of which is ratio tracking. And so the idea is to attenuate the contribution of each sample based on the ratio of absorption coefficient to the extinction coefficient, instead of terminating the path each time that you say that you have an absorption event. So we're avoiding the binary nature of the earlier delta tracking. So now, instead of terminating the path, when an absorption event happens, the contribution of the sample is multiplied by the inverted ratio of absorption coefficient. So more or less, the density becomes an albedo term. So this way, even if some of the light gets absorbed, it still contributes to the final image, just with a reduced weight. This helps reduce noise and improve convergence. So it doesn't help with this specific cloud example because the absorption coefficient is 0, but in general it can be useful. Also, since only the ratio of absorption to scattering coefficients matters, instead of declaring them separately, they can be merged into a single extinction coefficient density and an albedo color that defines the color. Albedo value. Instead of sigma A, sigma S, and color, there's just a sigma T and an albedo A. So now the equivalent of 0.5 absorption coefficient, 0.5 scattering coefficient, and a white albedo would be sigma T equals 1, and albedo is gray. This makes it easy to define the medium's properties since only 2 parameters need to be considered instead of 3. So transmission being updated. Did I say what W is? I think it's the throughput. But yeah, it's just this attenuation at each scattering event. Ratio tracking applies to homogeneous volumes just as well. You can see reduction of variance. So doing that versus just killing the ray when it would be absorbed. This can also be used for transmittance calculation in heterogeneous volumes. Instead of returning a binary result, of 0 or 1. Transmittance can be accumulated along the ray by multiplying it by the inverted ratio of actual extinction coefficient to the maximum extinction coefficient. Okay, so that's the density read. T of D is initialized at 1, and then you successively apply that. Each time that a collision event occurs, the transmittance is updated, multiplying with that ratio again. Just adding ratio tracking alone is not enough to make delta tracking fast. Performance is worse. It's because now the path is not terminated when the absorption event occurs, so the number of scattering events per path increases significantly. This leads to more computations and slower rendering times. So, to combat this, Russian roulette can be used to probabilistically terminate. We do this for paths that contribute very little to the output image. It is to randomly decide whether to continue or terminate based on contribution weight. If the weight is below a certain threshold, the path can be terminated. And if the decision is to continue, the weight of the path is scaled up to account for the probability of termination. This helps reduce the number of samples, especially with high variance scenes. After every scattering event, contribution weight W is evaluated. Random numbers, that's sigma, uniformly distributed is generated. If it's less than the probability of termination, the path is terminated. Otherwise, the weight is scaled up by dividing by the probability of Russian roulette termination to account for it. So if W is the contribution weight after a scattering event, the Russian roulette step updating it is that it's 0 if you pass or you fail this check, terminate. Otherwise, it is scaled up with that term. Expected value remains the same, so the image will converge to the same result eventually. So as long as probability of termination is chosen wisely, the Russian roulette term can significantly speed up rendering times and remain unbiased. PR to the highest value of one of the color channels seems to work well. Same can be applied to transmittance calculation, but in that case, the probability of termination can be set to the transmittance value itself, since there's no color channels. As mentioned before, we don't do much in the specific cloud example because the absorption coefficient is 0. If you have a non-zero absorption coefficient, that could be a benefit. Okay, so subdividing regions. We're talking about the biggest issue with delta tracking is that in volumes with a lot of empty space, many null collisions will be sampled before a real interaction occurs, and so that means a lot of wasted time. To mitigate this, the volume can be subdivided into smaller regions, and each one can have its own maximum extinction coefficient. This way, when the ray enters a new region, the maximum extinction coefficient can be updated to better match the local density of the medium, reducing the number of null collisions in empty regions. So if we subdivide the volumes into 32 by 32 by 32, too many, it becomes very dense. So for each region, maximum density value is computed and used to calculate the maximum extinction coefficient for that region. During the tracking, when the ray crosses into a new region, it updates with the new value from the grid. Significantly reduces the number of null collisions since the empty regions are skipped almost immediately instead of sampling null collisions. So without subdivision, a lot of time spent in empty space, whereas if you can skip that, it's a good thing. Every time a null collision is sampled, the brightness of the pixel is incremented. So the darker the image, the better. So, right, there's a lot of checking here in negative space versus not over here. That's because be able to locally establish a lower density volume, which means that you can make larger steps in these negative spaces. Because if you're using a single global maximum density somewhere inside the mesh or the shape or whatever, and then you apply that constraint to the entire grid, then you have to treat this entire space as if it had that same maximum density. But yeah, splitting it out into multiple regions avoids that. So with subdivision, render time is significantly reduced, stays unbiased, small amount of VRAM for the additional grid. Since most of the volume in the cloud is empty, it also benefits greatly. So 10 samples per pixel only takes 14 seconds, down from 248. So, biasing the sampling. Since clouds are really dense, really big, and highly anisotropic, they produce a lot of scattering events over really short distances in a similar direction. This means that most of the time, the amount of rays that have to be traced per path is huge, which increases the variance and render times. The design and evolution of Disney's Hyperion renderer proposes a solution. As the ray progresses through the medium, the density of said medium is lowered alongside the anisotropy. So this way, the sample distance becomes a lot larger, and the amount of rays per path is reduced, which reduces variance and speeds up conversions. Since the anisotropy is also reduced, the final image still looks somewhat correct. This does introduce some bias, but the visual difference is pretty minimal. So they're saying that they reduce the density and anisotropy linearly between the 5th and 20th bounce. So that's changing the scattering coefficients to take longer steps, I guess. Interesting. Okay, yeah, So it's becoming more of a uniform volume, lower density uniform volume over bounces. So they have expression for the anisotropy like this, based on the depth. It's the bounce count. And same idea with ray depth. And so they're manipulating the actual parameters used during the tracking changing it between bounces. Okay. So there's a bias factor between 0 and 1 that they're using to tune this. So 0.8 is what they're using. So with those couple of optimizations, they're down to 1.1 seconds instead of 248. Image is a lot less noisy, and the paths are shorter, meaning less variance. Visual difference is minimal. It's a little bit brighter because of the reduced noise. Without biasing, there is some very high frequency noise that makes the cloud look darker on low sample counts. Yeah, it's just a little bit of noise. Did an experiment with ways of reducing density and isotropy. Worth exploring further. Possible optimization is to calculate direct lighting only at the first and last scattering events. That way, number of light samples per path is reduced. Visual difference is minimal since most of the direct lighting contribution comes from the first and last scattering events anyway. That's interesting. Huh. So they're doing a summary of their optimizations using ratio tracking, Russian roulette, subdividing the overall volume, and biasing the sampling. They were able to get it down a lot. And there is the final cloud render. Still computationally expensive. So about 1,000 seconds. And it looks pretty damn good. So yeah, and then they mentioned also that it can be reduced a lot with a denoiser as well.